What's up everyone, it's Stack Lessons here. Welcome back to the channel. Today we're diving into Amazon Web Services DMS, EMR, and database migration patterns. Let's get into it. By the end of this video, you'll know exactly when to reach for DMS, when to pair it with SCT, and how to configure an EMR cluster without losing data or money. And these patterns show up across multiple questions on the Amazon Web Services Certified Data Engineer Associate exam. Here's the catch: one wrong qualifier word in the question flips the entire answer, and most candidates miss it on the first read. Picture this. Your CTO walks in Monday morning and says the Oracle database needs to be on Aurora-PostgreSQL by Friday, and the customer-facing app cannot have a maintenance window. That single requirement, different engine on each end, plus zero downtime, is the exact problem DMS and SCT were built to solve together. Get the tooling right and the migration is boring. Get it wrong and you lose a weekend, or worse, lose data. Let's get the scope of DMS right, because this is where most candidates lose points. DMS moves data between databases, tables, and their primary keys, full stop. First constraint. It does not migrate your secondary indexes, foreign keys, stored procedures, triggers, or views. Second constraint. It does not translate Oracle's PL/SQL into PostgreSQL's PL/PGSQL. Those two gaps together are exactly why a second tool exists, the Schema Conversion Tool, or SCT, which acts as the companion to DMS for heterogeneous work. Here's how Amazon Web Services describes the core capability. DMS performs continuous data replication using change data capture, or CDC. It tracks data that has changed and provides it as a stream of changes that downstream systems can consume. In practice, this means DMS reads the source database's transaction log directly, bin log for MySQL, write-ahead log for PostgreSQL, redo log for Oracle, so it captures every change without adding query load to the source. Here's how the zero downtime trick works. You point DMS at your source database, which stays online and serving traffic the entire time. Phase 1 is the full load. DMS does a bulk copy of every existing row into the target. While that's running, transactions are still happening on the source, so phase 2 kicks in. CDC reads the transaction log and streams every insert, update, and delete to the target, keeping it in sync. When the lag drops to near zero, you flip the application over to the new target and you're done. The source never went down. Think of it like moving house while still living in the old one. The moving truck, that's the full load, takes every piece of furniture you own to the new address. Then a courier, that CDC, keeps shuttling any new mail or packages that arrive at the old place until you finally hand back the keys. You never had to sleep on the street. On the left, DMS is the moving truck. It carries the rows, it handles full load and CDC, and it works for both homogeneous and heterogeneous data movement. But it does not touch your schema, your code, or your procedures. On the right, SCT is the architect. It converts your DDL, your PL/SQL, your triggers, your views, your stored procedures into the target dialect. It even produces a migration assessment report flagging anything it can't convert automatically. For heterogeneous migrations like Oracle-to-PostgreSQL, you run SCT first, then DMS moves the data. Here's the decision rule. Different database engines on each end. SCT first to convert the schema and the code, then DMS to move the data. Never one without the other. This is the single most common DMS trap on the exam. A question describes Oracle moving to PostgreSQL, lists DMS as an option, and candidates pick it without realizing SCT has to run first. Here's a pattern the exam loves. Nexer Retail has an RDS MySQL database holding orders, and the analytics team wants those orders queryable in the data lake. Instead of building a glue job, you point DMS directly at S3 as the target, set data format to Parquet, and DMS writes columnar Parquet files straight into the bucket, date partitioned by commit time. Once those Parquet files land, Athena can run serverless SQL against them instantly, with no ETL pipeline needed. A moment later, Redshift Spectrum can layer traditional warehouse queries on top of those exact same files. And for deeper batch workloads, EMR or Glue can pick the files up directly for heavier processing. One gotcha though, the defaults write a new file every 60 seconds, which produces thousands of tiny files that wreck Athena performance. Tune the CDC minimum file size setting to 64 megabytes, and the problem goes away. Let's wire up the keyword to answer mapping. If the question says the source must remain online, that's full-load plus CDC. If it says continuously replicate changes, that's CDC reading the transaction log. If it names two different engines like Oracle-to-PostgreSQL, that's SCT first, then DMS if it wants database data landing in S3 for analytics. That's DMS with an S3 target in Parquet format. And if it's a bulk one-time load with no ongoing changes, that's DMS full load only, and watch out for scoop on EMR as a distractor. Now let's switch gears to EMR, which stands for Elastic MapReduce. EMR is the managed cluster service for the full Hadoop ecosystem: Spark, Hive, HBase, Presto, Flink, Hudi, and scoop. You pick the instance types, the software versions, and the bootstrap actions, full control that Glue's serverless abstraction doesn't offer. The exam focuses on 3 node roles, and each role has very different rules. Reach for EMR when Glue's serverless Spark simply isn't enough for the workload. 3 roles. The master node, just one of them, runs the Yarn Resource Manager and the HDFS name node. It coordinates everything, and if you lose it, the cluster dies. The core nodes do 2 jobs at once. They run compute tasks, and they store HDFS data blocks on their local volumes. The task nodes are pure compute. They run Spark executors, but store nothing persistent, so losing one just means Yarn reschedules the work somewhere else. Now here's the Yarn detail that matters. When you submit a Spark job in cluster mode, the Yarn application master, which hosts the Spark driver, runs in a container pinned to a core node by default. Exactly so spot reclamation on task nodes can't kill your driver. That's why the purchasing strategy is master and core on demand, and task on spot. Picture a restaurant. The master is the head chef. There's only one, and if they walk out mid-service, the kitchen shuts down. So you never hire that person on a 0-hour contract. The core nodes are the line cooks who also own the pantry. Fire one and you lose the ingredients. The task nodes are temp dishwashers. If one quits mid-shift, you call another and dinner keeps moving. That maps one-to-one to the spot rules. Straight from the Amazon Web Services EMR documentation. Removing HDFS daemons from a running core node or terminating core nodes risks data loss. Use caution when configuring core nodes to use spot instances. That's Amazon Web Services being polite. In practice, if you care about your HDFS data, core nodes go on demand. Period. Here's why the task on spot rule is worth memorizing. On-demand price is your baseline. Call it 100% of the published rate. Spot price lands around 30% of that figure, which means a 70% discount on those task nodes, sometimes as much as 90% for less popular instance types. Now, the key question is how often spot gets reclaimed. The typical spot interruption rate on EMR workloads sits under 5%, thanks to capacity-optimized allocation. So on task nodes, where an interruption costs you nothing but a rescheduled task, You get massive savings for almost no risk. Where should the data actually live? HDFS is like storing photos on your laptop's hard drive. It sits on the EBS volumes of your core nodes. It gets replicated 3 times, so you pay for every copy, and the moment you terminate the cluster, it's gone. Useful for shuffle and intermediate data, terrible as a system of record. EMRFS, on the other hand, is like iCloud. Your data persists in S3, independent of the cluster lifecycle. No 3 times replication overhead, roughly 12 times cheaper per gigabyte, and multiple clusters can share the same data. That unlocks the transient cluster patterns: spin up, run the job, terminate, the data stays. Amazon Web Services states the architectural principle directly. EMRFS decouples storage from compute, so you don't need to provision core nodes specifically to store data, and you don't pay for replication in HDFS. When a question mentions transient clusters, sharing data across clusters, or terminating clusters between jobs, the answer always involves EMRFS and S3, not HDFS. Now the big decision: Glue or EMR? Reach for Glue when you're doing standard Spark or PySpark ETL, when you want serverless with no cluster operations, when Glue data catalog integration matters, and when your workload fits within Glue's worker limits. Reach for EMR when you need Hive, HBase, Presto, Flink, or Hudi, anything beyond plain Spark. Also reach for EMR when you're lifting and shifting an on-prem Hadoop workload, when you need custom Spark tuning that Glue's abstraction doesn't expose, or when you need very large memory. Glue's largest workers top out around 256 gigabytes of RAM, while EMR can run on EC2 high memory instances with up to 24 terabytes. One line to remember: serverless ETL means Glue. Hadoop ecosystem tools or extreme tuning means EMR. If the question names Hive, HBase, Presto, or Flink, that's EMR automatically. If the question says least operational overhead with plain Spark, that's Glue. Let's walk the traps that quietly cost points. DMS alone: for Oracle-to-PostgreSQL, you need SCT2. EMR master on spot, 1 reclaim kills the cluster. Core on spot with HDFS as the record, spot interruptions mean lost data blocks. EMR for plain Spark ETL, Glue handles that serverless. DMS writing default tiny files to S3, Athena performance collapses. And scoop on EMR when the question requires ongoing CDC, DMS wins that one every time. One more decoder for the full pattern. Heterogeneous migration means SCT plus DMS minimal downtime, or source stays online means DMS full load plus CDC. Database data into an S3 data lake means DMS writing Parquet directly. Transient cluster or sharing data across clusters means EMRFS with S3 as persistent storage. Lift and shift on-prem Hadoop means EMR, not Glue. And cost-optimize EMR compute means task nodes on spot, master and core staying on on-demand. Match the phrase, pick the answer. 7 things to lock in. DMS moves data, SCT converts schemas, heterogeneous needs both. Full load plus CDC, bulk copy first, then transaction log replication. DMS to S3 in Parquet, tune the CDC minimum file size to avoid tiny files. EMR master, on demand always. EMR core stores HDFS, so spot risks data loss. Task nodes are the spot sweet spot. EMRFS puts persistence in S3 transient clusters, decoupled storage. In Glue for serverless Spark ETL, while EMR covers the Hadoop ecosystem and deep tuning. All right, question 1. A company is migrating a 2 terabyte Oracle database to Amazon Aurora PostgreSQL. The application cannot be taken offline. What is the correct approach? Is it A, use SCT to convert the schema, then DMS with full load plus CDC for the data? B, use DMS with full load plus CDC only. C, use DMS to export to S3 in Parquet, then load into Aurora. Or D, use Glue to run a Spark job that reads from Oracle and writes to Aurora. Take a moment to think about it. The answer is A. Oracle to Aurora PostgreSQL is a heterogeneous migration, different engines on each end. DMS moves data, but it does not convert schemas, stored procedures, or PL/SQL. SCT must run first to translate those into PL/PGSQL. Then DMS handles the data with full load plus CDC for the zero-downtime cutover. Question 2. An EMR cluster runs nightly Spark batch jobs. The team wants to cut compute costs by 60% without risking data loss or job failures. Which purchasing strategy is correct? Is it A, all nodes on Spot? B, master on Spot, core and task on on-demand? C, master and core on on-demand, task on Spot? Or D, master on on-demand, core and task on Spot? Take a moment. The answer is C, master must always run on demand. If it gets reclaimed, the entire cluster dies. Core nodes store HDFS blocks and host the Spark driver, so Spot interruptions their risk data loss. Task nodes store nothing persistent, so a Spot reclaim just causes Yarn to reschedule the work. Master and core on on-demand, task on Spot is the textbook pattern. Question 3. A data engineer needs to replicate ongoing changes from an RDS MySQL database directly into an S3 data lake in a columnar format for Athena queries. Which solution minimizes ETL effort? Is it A, run a nightly Glue ETL job? B, configure DMS with full load plus CDC and an S3 target with data format equals Parquet? C, use Kinesis data streams to capture binlog events, then firehose to S3. Or D, use scoop on EMR every hour. Think about it. The answer is B, DMS supports S3 as a target with data format set to Parquet. Writing both the initial bulk load and ongoing CDC changes directly to S3 as columnar Parquet files. No separate ETL pipeline needed. Athena and Redshift Spectrum can query the data immediately. Just remember to tune CDC min file size so you don't end up with thousands of tiny files. Question 4. A team needs to run interactive Presto queries, schedule Spark ETL jobs, and host an HBase cluster, all on the same managed platform with full control over instance types. Which service fits? Is it A, Glue with multiple jobs and crawlers? B, Athena with federated queries? C, EMR with Spark, Presto, and HBase applications? Or D, Lambda with step functions orchestration? Take a moment. The answer is C, Glue is limited to Spark and PySpark ETL. It cannot run Presto or HBase. EMR is purpose-built for the full Hadoop ecosystem, including Spark, Hive, HBase, Presto, Flink, and Hudi, with full control over instance types and configurations. When the question lists Hadoop ecosystem tools, the answer is EMR. Question 5. A company wants to share processed S3 data across multiple short-lived EMR clusters without reprovisioning storage each time. Which approach enables this? Is it A, store the data in HDFS on the core nodes and snapshot before terminating? B, replicate the data across task nodes using HDFS replication factor 3. C, keep one long-running EMR cluster and run all jobs on it sequentially. Or D, use EMRFS with S3 as the persistent data store and launch transient clusters per job. The answer is D, EMRFS decouples storage from compute by keeping data in S3. So any number of transient EMR clusters can read and write the same data without reprovisioning. HDFS lives on the cluster and dies with it, so option A loses data the moment the cluster terminates. Task nodes don't store HDFS data at all. And keeping one long-running cluster wastes money when jobs are intermittent. EMRFS plus transient clusters is the textbook pattern for decoupled storage. And that's a wrap on Amazon Web Services DMS, EMR, and database migration patterns. If this helped you out, smash that like button and subscribe for more. See you in the next one.